Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, Senior 4 Chemistry students. Welcome back. Alan is my name, still with you in chemistry lessons. We are still on Unit 17, which is about reduction and oxidation reactions. That is under the overall topic of electrochemistry. Electrochemistry, electron, meaning we're involving the movement of electrons. So today our lesson, we are heading in for lesson 3, and that is determination of oxidation states or oxidation numbers of an element in different compounds. So that is what we're going to look at in details and try some more questions and some exercise for us to test our understanding. As usual, I always give an outline of what we shall focus much, the key terms for you not to miss in the lesson, and the crucial learning objectives to achieve. So, starting on what we shall be covering in this lesson specifically will be much more on the calculations involving oxidation numbers, that is assigning and then performing calculations or carrying out exercise and activity. Then when we're done identifying the oxidation number, then we can go on and identify the reducing and oxidizing agent. Remember, we defined those terms, or oxidizing and reducing agents, in our lesson 2, which we shall quickly make a quick highlight. But in this case, we are going to use oxidation numbers to identify which species has been oxidized and which species has been reduced. And it's on that basis that I bring unto you the key terms. One is the oxidation number. We also defined it in lesson 2, but it's still a key term in here, since we shall be working out the oxidation number. So it's still a key term for you not to miss out, and understanding what is a reducing agent and oxidizing agent, basing on the changes in the oxidation states or numbers for each component. So those are the key terms, and as a result, by the end of the lesson, you should be able to apply correctly the rules and guidelines in determining the oxidation numbers of different atoms for different elements in compounds and in ionic aspects. So that is what we're going to look at, how to determine and assign oxidation numbers. So, a quick review, as I was mentioning, of lesson 2. If you missed the lesson 2 content, this is a quick review of what we looked at, but I would still implore you to go back and find that content, and you do not miss a lot. So in lesson 2, we looked at the different components of a redox reaction, and what are they? A half equation and overall equation, then the different aspects of a reducing agent and oxidizing agent. Going on to the half and overall equation reactions, a half reaction has only one side of either reduction or oxidation. And of course, when we talk of oxidation, we meaning losing of electrons, and reduction, talking of gaining of electrons. So when you combine the oxidation half side and the reduction, then they give us what we call a redox, which is the overall. Reduction, oxidation, redox. equation or redox reaction. So when an atom loses electrons under oxidation, then its oxidation state increases, and when it gains, then its oxidation state decreases, meaning it is becoming more negative because of more electrons it has gained, and it becomes more positive as it loses due to more protons. So those are what we looked at. We ended on by saying an oxidizing agent accepts electrons and it gets reduced. Of course, as it accepts electrons, its oxidation state will decrease, and that is what we mean by, its oxidation state will decrease, and that is what we mean by being reduced. Then reducing agent releases electrons, and so its oxidation state increases, and in that way it becomes oxidized. That is what we looked at. Then we ended up with a homework which was to test our understanding in terms of oxidizing agent and reducing agents. And what we looked at, we said this side is mainly oxidizing and this side is mainly reducing. So we have reducing agents, we have oxidizing agents. So we had gone through question 1, so let me not waste much more time. Let's start on question 2 or part B. Which of the following reactions would occur and explain? Remember, we are doing corrections. So if you're having blue reacting with green, will there be a reaction? This is an additional of your periodic chemistry. So we are transferring knowledge of periodic chemistry into in here. Group 4, as you can see, and group 7. Yes, the reaction will occur. We expect group 7, or this green, to gain electrons from blue, which is in group 4, since the oxidizing abilities increase across the period, meaning the green has more oxidizing abilities than the blue, so it will tend to pull electrons from blue. And of course, from their position, you notice this would be covalent, but it is a polar covalent because of the pulling effect of the group 7 element, which is green. So yes, the reaction will occur, and the explanation is that one. Lastly, if you have red, which is a group 2 element, reacting with green, which is a group 7 element, automatically the reaction will occur, as you can see. Red will lose electrons, forming positive 2, and the green will gain electron, forming -1. So yes, the reaction will occur because red is a reducing agent and green is an oxidizing agent. So you see how you can easily tell, considering their oxidizing and reducing abilities, how you can easily tell the reaction which will occur. So that was the assignment I had left you with, just basing on oxidizing and reducing aspects, or what we would call a redox occurring. That is it for that. We can now get started on our lesson 3 activity. So I prefer starting with this activity. It will help us conceptualize the significance of oxidation states, or oxidation numbers. So take a look at activity 1, lesson 3, our current lesson. You have a minute to just read through, then we can find the way forward. Take a minute to read through. Question 1 reads, determine whether the underlying species has undergone oxidation or reduction. And what is that underlying species? In A, it is carbon, or C, this is carbon in methane and carbon in carbon dioxide. So we are to determine whether it has undergone oxidation or reduction. B, it is iron. So for us to quantify that, we must carry out a determination of oxidation number to know the changes that are happening. Look at question 2. Which species is oxidizing and which one is reducing? Again, we can't identify oxidizing agent or reducing agent in an equation unless we've quantified the changes in oxidation numbers. So, meaning, for us to understand this and do the whole of these questions, we need to first have the understanding of oxidation numbers and how they are calculated. Now, this takes us to determining oxidation number. Remember, when we know oxidation states or oxidation numbers, as it is increasing or reducing, then we can identify whether it is a reducing agent or it is an oxidizing agent, or whether it has undergone oxidation or whether it has undergone reduction. So the whole big picture to look at is the changes in oxidation numbers. Oxidation number was defined by R.U. Parker, basically, if I can paraphrase, as the number of electrons an atom is assumed to have either gained or lost in chemical bonding. And when we talk of losing or gaining, we are bringing in the aspect of ionic bonding, losing and gaining. But of course, we know this is not always true for all components. Some components do not completely lose, and others do not completely gain. That is where we have covalent bonding. But when we're looking at oxidation numbers, we only consider all bonds to have been ionic. Atom has lost electrons, and the other has gained electrons. So the charge that is attained when that happens is what we consider as the oxidation number. That's a quick review because we defined that in details in lesson 2. So what are the guidelines for determining the oxidation numbers of different components? So let's look at those. The first prominent, which you should never forget, are these. 1, any element in its elementary form, its oxidation number is 0. Because it has not lost or gained the electron. So it is still having equal number of protons and neutrons. So it is not having any charge in simple. So if it is in elementary form, its oxidation number is 0. What do we mean by elementary form? Some elements exist as solids, some as gases. That's what we mean. In its elementary state. Sodium is a solid. So in its elementary state, it is 0. Hydrogen is a gas as H2. Mercury is a liquid. So when it is in the liquid state, when it has not ionized or it has not lost or gained electrons, then it is having 0 oxidation state. I think that is very clear and understood. Let's look at number 2, or the guideline 2. Group 1 and group 2, they have oxidation number as +1 and +2, respectively. What do we mean? I'm still going to use the example of sodium, which is in group 1. It loses 1 electron to be stable, and in the process, it will only form +1. Let me quickly illustrate that. Let me illustrate the oxidation state of sodium. What do we mean? And even magnesium. Remember, this has 11 electrons, this has 12 electrons. So, if we can use our ordinary understanding very, very, very fast, this is sodium with 2 electrons and 8 electrons in here, then 1 electron, and this is magnesium Remember, these are the energy levels. 2 electrons, 8 electrons, and 2 electrons in the outermost shell. So by saying group 1, this is an example of a group 1 element. This is a group 2 element. So it loses this 1 electron to have a stable electronic arrangement, and it forms positive 1. This forms magnesium, positive 2. So as it loses 1, it will have a single positive. So it can't lose any more of the electrons because it has attained a stable electronic configuration. So group 1 will always have a positive 1 because they easily lose electrons, the outer electron, to form a positive 1. Group 2 lose 2 electrons to attain the stable electronic configuration with octet arrangement. So in this case, for any group 1 and group 2 will always have a positive 1 and positive 2, respectively, because we have high tendencies of losing 1 electron and losing 2 electrons. I think that is very understandable. For hydrogen, it's always positive 1. It has 1 electron, so it easily loses that 1 electron. If it is bonded to more electronegative atoms. Then if it is bonded to these metals, which easily lose electrons, then it is having a -1 because it has gained the electron from the metals. One more other aspect before we can try a few examples is in a compound, if you have more electronegative atom and a less electronegative atom combined together, then the more electronegative atom will have a negative oxidation state because it will gain electrons. Then the less electronegative, it will have a positive oxidation state because it will lose electron. If you can use an example here like magnesium chloride, chlorine is more electronegative, magnesium is less electronegative. This has a positive value, this will have a negative value. This is what we mean by that component. And as such, there are crucial aspects that you should not forget when it comes to electronegativity tendencies. Fluorine being the highly electronegative element, it will always, quote that statement, always have -1 because there is no any other atom that can take electrons from fluorine. So it will always have -1. Why -1? Because it gains that 1 electron to form a stable oxidation state. Then chlorine, bromine, and iodine being in group 7, which are relatively highly electronegative, they always have -1 on condition that they are bonded to a less electronegative atom. But if they are bonded to a more electronegative atom, then they become positive. What are the examples of more electronegative atoms? We have oxygen, nitrogen, fluorine. That's why I brought in chlorine in this case. Chlorine being more electronegative compared to bromine and iodine, when it is bonded to iodine or bromine, then chlorine attains a negative. These two attain a positive oxidation state. Simple, apply the electronegativity, which you already covered. One more last aspect, oxygen will always have a -2. Remember, it is the second electronegative atom, as you see. So it will always have a -2. Why -2? Because it requires 2 electrons to gain the stable electron configuration. But there are exceptionalities. One of them is if it is bonded to hydrogen in the peroxides, then it is having a single -1. These are shared. Let's look at peroxides, if I can quickly illustrate that. H2O2. This is HOOH. H bonded to oxygen, oxygen, hydrogen. So you notice we have oxygen, oxygen, which are equal in electronegativities, so in meaning there will be no electron gained by one atom. But instead, it gains an electron from hydrogen and hydrogen. That's why it has -1. And of course, hydrogen will have a +1 and a +1. And this is a -1. So these are the principles we're going to be applying. I'm quickly explaining what they imply. Okay, so let's check up what we've looked at. And the quick check is that question. A quick check is that question. Magnesium ribbon reacts with dilute hydrochloric acid according to this equation. You see, this is a compound, this is a compound, and so on. With a reason, assign each atom its appropriate oxidation state. Assign each atom its appropriate oxidation state. I will help you, take you back in there for you to refer to the guidelines as you assign the oxidation state. I'm giving you 30 seconds. Reread the guidelines, then you attempt. Read the guidelines, then you attempt. Take some 30 seconds to quickly attempt that. That's the question. All right, I hope you've obtained the answer. Now, let's compare with the answer I have. What do you notice? Magnesium is given a 0 because it is in elemental state, it is in the pure form. Hydrogen being bonded to chlorine, which is more electronegative, it will have a positive value. This is a nonmetal. Chlorine will have a negative because it is gaining an electron from hydrogen. Magnesium, since it is in group 2, will have a +2. It loses 2 electrons. Those 2 will be gained by chlorine, so meaning in here chlorine still, each chlorine has a minus. And lastly, hydrogen, since it is a gas, look at the states. Since it is a gas, then it will have a 0. That is how you can quickly apply those oxidation, the guidelines in the determination of oxidation numbers. That is a quick check for those 7 principles. Now, let's add more principles. They are actually 3 remaining, then we can try some numbers. So if you're having a compound, still like magnesium chloride, if it is not charged, then its total oxidation number will be 0. Why? If we can use this, magnesium, it is having +2. Chlorine, each chlorine is having -1, but they are 2 atoms, and this gives +2 plus -2, which is 0. That's what we mean by saying for electrically neutral compound like magnesium, the sum of oxidation numbers is 0. This is what it implies. So if you have the ion, of course ions are charged species. It has either gained or lost. If it is a single ion, then its oxidation state is the charge on that ion. An example is well illustrated in here. Lastly, if you're having the ion which is having many atoms, then there are a few principles that are followed up. I'm going to use, I will not read everything, I'm going to use the example here. Let's look at polyatomic ions. an example, we're using the sulfate. It has many atoms involved in. So in this case, how do we quantify or how do we get the oxidation numbers of this? First aspect is we look at which one is having the higher tendencies of gaining electrons. That is more electronegative, which is oxygen. So oxygen will attain a negative, sulfur will attain a positive. So what kind of a number will we give to sulfur? Because it is bonded to a more electronegative atom, sulfur will take the outermost shell electrons. It will take a positive value for the whole of the outermost shell electrons. In this case, sulfur is in group 6, so it will take a positive 6. It takes a positive 6. Then oxygen will, of course, take a -2. Wherever it is, will always be a -2. We are having this charge in here. So when you are looking at the sum of the whole oxidation numbers for this molecule, then you involve the calculation which says the sum of these molecules is equal to the charge of that ion. In this case, we've already identified our sulfur as +6, oxygen as -2, but they are 4 oxygen atoms, so this will be -2 times 4, which is -8, +6 plus -8 directly gives you a -2, as it is clearly done over here. So those are the guidelines, and for you to understand them, it's best you practice them. So I will leave you with that quick check. I'll call it quick check 2 for you to try and come up with the answers to help you understand these guidelines. Thank you for taking part in the lesson. Please go through that quick check 2 for you to understand all the guidelines. We meet in the next lesson. Please stay safe. Bye.